Welcome to Simplified Astrophysics. In this lesson, I'll be explaining how we can find out the distances between us and objects in space. Now, there are two main ways we can do this, using angles and using flux. So let's look at how we can do this using angles. So let's say I have a circle, and in the center of the circle is us, Earth. And we can make a sector here with these being r, which is the radius of the circle, and the middle angle being theta. So I can split this into a triangle where this length is equal to L and the length of the arc we can put as equal to S. So in astronomy, we know that R will be much larger than L. So this will imply that L is equal to S. Now if I took this triangle and made a different diagram here, and this place is the Earth, again, this point, and this would be L, which is equal to S in our approximation. So if we were to put a straight line and name this distance d, then due to the very large scale of things in space, we could approximate r, the radius of the circle, to be equal to d. And we could find out the value of d using the equation L equals d theta, which implies that d is equal to L by theta. So what's the other way we can do this? Using flux. So if I were to draw another circle, and this time I'll put the sun in the center. And the sun, it was giving off lots of light, obviously, right? So we could define the distance between the sun and, let's say, a telescope on Earth with a detector at the back. And this length would be d. So we find that energy per second, the formula for that would be luminosity of the sun. That's the amount of, basically, the amount of light it gives out. So the power, the unit is watts, into the area of the cross-sectional area of the telescope over here, whatever the light is hitting. That would be area divided by 4 pi into d squared, which is the distance here. Now, this value of A is really uncertain because it's different for every single telescope. So what astronomers do is they take this A and they bring it over here. So that becomes E by AS is equal to L by 4 pi d squared. Now this, we can write it as F, which is the flux. Now, as you can see based on this equation, flux is defined as the energy per unit area per second. Now, using this detector on the telescope, we can find out the value of this flux when we look at a certain star or portion of the sky. So we can write this final equation as F equals L by 4 pi d squared. Now let's try a sample calculation. What if we wanted to find out how far away the sun was from us? Now we know that the luminosity of the sun is equal to 3.846 into 10 to the power 26 watts. And let's say our telescope on Earth measured a flux of 1400 watts per meter square. Now, using our equation, F is equal to L by 4 pi d squared, we can rearrange to make d the subject, and that gives us d is equal to root L by 4 pi f. And plugging in our values here, we get d as 1.478 into 10 to the power 11 meters, which is roughly equal to 1 astronomical unit, which and we see that 1 astronomical unit is actually defined as the distance from the Earth to the Sun. So this is pretty consistent. So we know that this formula works.